Okay, now that we know a little bit about the circular motion, centripetal acceleration, and the centripetal forces, the best way to learn more is doing problems. So I picked problem number 51 from page 135, and I have taken a picture of the problem, and then I have attached to it. So now is a good time for you to pause the video and read this problem. And after that, even without restarting the video, I would like you to take a paper and mark all the forces acting on the plane. So it says the wings are tilted at an angle of 40 degrees. So here the theta angle given to us is 40, we know that. And the radius of the circle in which the plane is flying, that's what we are to find. So we just have to draw a circle, and I'm just drawing a side view of the circle. If you actually look, if you keep your eye over here, like somewhere over here, and look down, then the view would be something like this. Down here I'm drawing that. So here is the plane, and this is the center, and if you place your eye the place where I have placed it, you will see that the plane is moving in a circle. The radius is r, right? I mean, this is actually, the second one is not a very clear picture, so I'm going back to where we were, and I can actually erase this picture for now. All right, that I don't want that. And then I am going to mark all the forces acting on the plane. So let's start with the weight. The weight is directly pointed down, no matter what. Inclined plane, whatever, the weight is pointed down. And then it says there is a lifting force, aerodynamic lift, and that is perpendicular to the wing surface. So you can see that the wing surface, if I just draw this line, that is the axis of the wings, and the lift force using the same blue is perpendicular. I don't know if it is perpendicular enough, but you know, this angle is 90 degrees, that angle is 90 degrees, and I'm going to call this force aerodynamic lift, FL. So we are supposed to find the radius. Now we have two forces, and we have a circular motion, and so we are going back to the recipe given over here. I think you can, I'm going to read one by one. So first thing is, read the problem a few times, that we did, and mark the forces on the diagram. We did that. Draw a force diagram. Well, the force diagram alone would be something like this. This is the inclination of the wings. Actually, that inclination is a little bit higher than what the picture shows. That's okay. And then, as always, I like to make the object a little dot, and then here you have the weight pointed downward, and then you have the lifting force FL, and the radial direction would be like this. Actually, I don't want to draw it in that form. Let me erase that and then draw it using a dotted line, like dot 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 dot. So that is the same dot 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 over here. This is the direction of the center, and that is the radius r. Now the last step according to this is use Newton's laws. That would be sum of F equals to ma. Now we have this thing called like making these tables, and I'm going to go with those things now that we are back in problem solving. And so we have two forces, FL, and the other one is W, and so we have to take the x component of the lifting force and the x component of the Wx. So we have to find the angle. Now if you guys know that this to be a 40-degree angle, then that is going to be a 60-degree, a 50-degree angle, right? If this is a 50, then this is a 40. right? If this is a 40, then this becomes a 50 again, because this is perpendicular, that is perpendicular to the dotted line. And also if I draw this line, that also perpendicular in that form, that is also perpendicular, right? So, we have the angle. I think you can see them better now. The green square is 90 degree that FL makes with the plane, and then the red square is the 90 degree the W force makes with the positive x-axis or the radial direction. Okay, so let me get back to the tables here, and I have this blue arrow. The blue arrow points in the direction of x or toward the center. In this case, it's the same, toward the center. So I am going to take the components of FL. So you got FL cosine 50, and W here, W cosine 270. Actually, no, W cosine 90 or 270 or 90, it doesn't really matter. And then here the answer is 0, and here FL cosine 50, you can find the value of cosine 50 and plug it over here. And A sub C, that is the centripetal acceleration, we have that. We can call it V square over R, or simply AC. Okay, so this side we are going to make the white table, as I said before. So I just have to find my pen. Okay, so you can see that this is the white table. This is the white table, and then here you can see FL sine 50, and this is coming from the previous page, the force diagram, and then the Y component of the W, and if I actually want to, I can put Y component here, and then AY is 0. Now this is really important because there is no motion of the plane. If I take this to be the plane along Y direction. Now if you have a motion along Y direction, then it wouldn't actually go in a circular path as shown in the picture or as given in the problem. So I am going to use Newton's second law. Sum of Fy equals to mass times Ay, and FL sine 50 minus, actually let's say W sine 270 equals mass times acceleration 0. So you have FL sine 50 and W is mg, and sine 270 is minus 1, that equals to 0. So if I rearrange the equation, you will get FL equals to mg divided by sine 50. Now you have this as the second equation, and then the first equation, actually this is our first equation, and I'm going to use sum of Fy, sum of Fx equals to mass times acceleration, and this is coming from the previous table. Now what are the forces acting along the x direction or the radial direction? That would be FL cosine 50 and this side, and that's it. And this side you have mass times v square over r. So the reason that we are using a as our v square over r is because this ax is nothing but a sub c, the centripetal direction acceleration, or the centripetal acceleration. Now FL equals to mass times v square over r, and then cosine 50, that also goes in this side into the denominator. And so you have FL given in this form. There you have equation number 2. Now if you check equation number 2 and 1, they both have the same term on the right hand side, left hand side. So if you just replace the left hand side by the equation number 2, then you will get 1 equals to 2. Then you will get mv square cosine 50, m's are down here, and the other side mg sine 50. You know what? I'm going to quickly erase these numbers and change them to 2 and 1. Then actually that will be more consistent the way how I wrote it. That will be 2 equals to 1. So this is what you have from equation number 2, and this is what you have from equation number 1. So what happens is m cancels out, and we already know the value of the speed. The speed of the plane is given to us as 480 km per hour, 480 km per hour, and then you have to convert this into meter per second, and after that you can substitute. And if you take r to one side, you will have r equals v square sine 50. I mean all these things you know. Sine 50, cosine 50, you can find them using the calculator. And v you know, g you know, and all what we know pretty much everything on the right hand side. So you can find the value of the radius, and radius of the circle that the plane is making a uniform circular motion. And I think you followed everything that I did, and if you didn't, you can always go back and replay the video until you understand everything. I mean the force tables, nothing's new. We have done this many times in the past, and then only thing that is new here is we are replacing the centripetal acceleration by v square over r. So the problem wants us to find the radius. There are a couple of forces involved and a circular motion involved. So when that happens, you have to know what equations to use, and in there the only equations that are available in order to solve a problem like this are the Newton's laws and the circular motion laws, and the knowledge of using the centripetal force and finding the direction of the center of the circle that the object is moving around. And I'm going to pause this, and then once you are done watching this, you can actually watch it a couple of times if you want, and then I want you to do the problem all alone and then bring it to the class next time we meet.
Ravindu?